buy toys because we'll be going over to Sable Elementary School this coming Friday, and Santa shows up with us, and we give my club, Excalibur Club. No, you guys are staying here. Unless you're in Excalibur.
What's Excalibur?
It's the guys volunteer club that we have here at Creek. The guys volunteer organization here at Clear Creek.
Is it only guys?
Yeah, Big Sisters is the other club.
Big Sisters.
Big- So we've it was kind of fun walking around Target on Friday. We spent, how much did I say it was, Jay? Was it $1,400? $1,400 we spent at Target. 6 shopping carts mounded with toys for kids, and we came back here. We were here till 9 o'clock on Friday night wrapping toys. And so in my office, if you come to my office, there's a stack of boxes full of toys, all wrapped and ready and tagged for the kids at Sable, so Santa can give it to the kindergarten kids. So I thought it was pretty cool. If you would, let's get out that worksheet from last time that the assignment was on. I think it was the back page of the notes, right? I think so. All right. All right, let's run through these. Addie. Thank you. All right. You are taking a multiple choice quiz in English that has 5 multiple choice questions with 4 choices. You forgot to read the book last night, so you have no clue what happened in the plot.
Wait, what? Say it again?
I'm going over the homework.
Oh, I'm like, what?
So if you had it out, you'd be reading along with us. But you guess randomly on the quiz, find the probability that. So, so problem number 1, we have. Come on, baby. Find it. There we go. So we have. You have A, B, C, and D for your choices. I don't know. Maybe they have it labeled something else if they were multiple choice. Yeah, there's 5 questions total. Okay, so if you drew a tree diagram out of it, you have 5 choices. So here's question 1, question 2, question 3, question 4, question 5. So how many choices does each question have? 5, right? Or no, 4. A, B, C, D. Each question has 4 branches. So I have A, B, C, and D, and A, B, C, and D.
You put 1, 2, 3, 4, 4.
So I can't write a 5 these days. A, and B, and C, and D. And let's break this down a little bit. Extend the page so I can. This has A, B, C, D, A, B, C, D. So I'm just creating this big old tree diagram of our test. Okay? So, so we're basically, that's how our choices could go. If you were just to randomly guess, or, think to yourself, you go through. So let's think about this, how question 1 will go. If I have 4 choices, and I don't care about the test, I'm not prepared for the test, I look at the answers, and it looks like ants rolling around on a piece of paper. So if you have 4 choices, for question number 1, if there's only 4 choices and one of the answers is correct, what chance do you have at getting that question right? 1 out of 4, right? So you have a 1 out of 4 getting it right, or a 3 out of 4 getting it wrong, right? And we have the same thing for question 2, question 3, question 4, and then question 4, and then we change to question 5. I did that right. Does that make sense? Okay, so that's the probability you get it correct. So we want to find the probability, the chance that we get them all wrong. So I have a 3 1/4 chance of getting each of these wrong. If you have a calculator, it would be beneficial for me. But let's see if I can do this. I got 3 times 3, that's 9. 9 times 3 is 27. 27 times 3 is 81. 81 times 3 is 243, I believe. Somebody multiply that out. 3 times 3 times 3 times 3 times 3. And then 4 times 4 is 16 times another 4 is 64 times another 4. That's too much for me. What is 4 times 4 times 4 times 4 times 4?
4 times 4 times 4. That's like 2.
How much? It's big.
243.
243 is 3 times 3 times 3 times 3 times 3.
Wait, alright. 4 times 4 times 4. Wait, how many times 4 times 4?
I have 5 questions.
Times 4 times 4.
1,024.
Thank you.
1, 2.
Hey, will you do me a favor real quick? You have a calculator, so go 243 divided by 1024. So you can leave it like that, but just do that so we get the
243
divided by 1024.
It's gonna be a difference.
It sure is.
0.2373046.
Perfect. We're good. So, what is the chance that I get all of them wrong? I have a 23% chance of getting them all wrong. What? I'm sorry, what? It's still in here. Okay. So, I have a 23.7% chance if I just bubble randomly that I would get all of them wrong. Okay? So, you have a better chance of not getting them all wrong, right? Even if you guessed. So, letter B says you want to get all 5 right. Well, all 5 right is 1 times 1 times 1 times 1 times 1. I'll take care of that. No, it's 1, but good try. 1 out of 1,024. Will you go 1 divided by 1,024 on your calculator, please?
1,000 divided by 124.
1,024. It's a decimal still. That about right?
Yeah.
Okay, so let me ask you all this. Why do you have a lesser chance of getting them all right versus getting them all wrong? There you go. There's 4 options that take place. Of those 4 options, only 1 is correct. So you have a 0.097% chance of guessing all correctly. Ooh. Okay. And then, what is the probability you get at least 1 wrong? At least 1 wrong. So we're going to have to do a complement of something. So probability get at least 1 wrong. I did. Oh. We'll come back to that. I'm sorry. Thank you. Okay, so we get the first 2 right. And then the rest wrong. Okay, so what's the probability we get 1 right? 1 out of 4. What's the probability we get another 1 right? 1 out of 4. What's the probability we get the rest incorrect? That's 3 or 4 times 3 out of 4 times 3 out of 4. Because there's 5 questions, is that right? So that's right, that's right, that's wrong, that's wrong, that's wrong. Agree? So this is just saying we get, so 1 times 1 is 1, and then 3 times 3 times 3 is 27. 1 times 27 is 27. And then that's out of 1,024. Okay, and again, you can figure out on the calculator how to do that. You get at least 1 wrong. So that means you can get 1 wrong, you can get 2 wrong, you can get 3 wrong, you can get 4 wrong, you can get 5 wrong. So this was the probability we got them all wrong. So if I subtract that, so this is D, I subtract that, that comes out to 0.863. So you have an 86% chance that you get at least 1 wrong. And then the probability of getting at least 1 right, I'm going to do the complement at the top, so that's 1 minus that. Holy cow, so that's going to come out to 0.99. We'll just stick with that. You get about 99% chance that you get it at least one right.
Wait, what was C again?
C was, you get the first two right and then the rest wrong, was this one, 27 out of 1,024. Wow. And I was looking at the quiz. The quiz is going to be pretty generic. It's going to be a lot simpler than, you probably get the part A question, and that'll be about the extent of it as far as toughness goes. All right, you are rolling a die twice. So you have a single cube, 1 through 6. You roll it, check it, roll it again, check it. Okay, can I move on? So number 2, what is the probability? Okay, so you have, these are the outcomes that take place on a singleton die. They're all the same likelihood of showing up. Okay, what is the probability of observing 2 5s? So letter A, what's the probability of getting a 5 and a 5? Okay, so probability of getting a 5 is a 1 out of 6. Probability of getting another 5 is a 1 out of 6. So you have a 1 in 36 probability of that taking place. So you have a 35 out of 36 probability it won't take place. Okay, and I'm going to skip to number 3. Number 3, we're doing a Venn diagram. And basically on a Venn diagram you should have, so the outside rectangle or shape is kind of like those that don't fall into the Venn diagram. Okay, suppose the probability of finding a U.S. resident that has traveled to Canada is 16%, and to Mexico is 15%, and to both is 9%. So 0.09. So Mexico, Canada, both. Okay, so we have to account that 9% is part of the Canadian. So this will be 0.07. The reason it's 0.07 is if I go 0.09 plus 0.07, I get 0.16. And then Mexico is 15%, so I'm going to multiply that and make that 0.06. Okay, so again, look at your data. So if you take a look at how our circles work, I have this circle here, and then I have this circle here. And there's an overlap of the green and the purple. Okay, so that was 9% had gone to both. So being I had 16% that had gone to Canada, if I take that same 0.09 and add it to the 7, that 0.09 plus 0.07 is 0.16. And then we're for Mexico, 15% went there, so 0.06 plus 0.09 gives me 0.15. So you're talking about, if you were to add all that up, you're talking about 15, 20, there's 22%. So that means if there's 22% that went to Mexico, that would mean that 0.78 of the population didn't go to either of the countries. Doesn't mean they haven't traveled to another country, just they didn't go to either of those. Okay, travel to Canada, but not Mexico. Okay, if you traveled to Canada and you didn't go to Mexico, you're talking about this. So that's 0.07 went to Canada, but not Mexico. Okay, so 7%. Travel to either Canada or Mexico. So I'm not worried about if you went to both. You went here or you went there. So I went here or I went here. So that's 0.13 went to Canada or Mexico. It wasn't the combination of the two. So 0.13. That's not a B. That's a 0.13. So 13% of the population went one to the other. Not travel to either country. 0.78. Neither. And then not traveled to Mexico. Okay? So you have the 0.78 that hadn't been to either. And then what percent went to Canada? 0.13. Because they went to Mexico or Canada. They didn't go to both. Okay, so you add the 0.06 and the 0.07. So I'm going to take the neither, the 0.78, and the ones that went to Canada, which is 0.07. So 0.78 plus 0.07 is 0.85. So 0.85 have not gone to Mexico. 85% of the population. And again, this is fictitious data, so you can debate it all day long, and you're probably right, because we made it up to get to a thought process. Number 5, I think, is going to be a better tree diagram. Number 5, which is on the back side of the page. Due to a turnover and people who are absent, this assembly plant, factory, knows that 20% of the items are assembled by people who don't have experience, because they're new. Okay? So let's draw the first branch of our tree. First branches. So you have 20% that are the new people, and you have 80% of the things that are assembled are by the veteran, the people who have been there for a while. Okay, does that make sense so far on the tree diagram? So going with this, and then we're taking this from the first question. Due to a turnover and people who are absent from an assembly plant, 20% of the items are assembled by people who are inexperienced. So that means 80% of the product coming off the assembly line has some sort of person who has experience. So if you're having a hard time going, what is that? No experience and experience. Okay, now think about a tree diagram. If you add the limbs together, 20% is the same thing as 0.2. 80% is the same thing as 0.8. If I add those together, I need to come up with 1.0. Okay? Does this make sense still? Okay, management has determined that customers return 12% of the assembled by inexperienced employees, whereas 3% of the items that were returned were made by an experienced employee. So like they had some product and you were able to look at the bottom and there was some number and it's like, oh yeah, that's number 0.00335 employee, the brand new. Okay, so of the non-experienced people, there's a return and a keep. So this branch here says that 12% as a decimal is 0.12. Is that right? So that means that 0.88 of the people who buy this product don't return it, even if it was made by somebody who didn't have experience. Maybe it was made correctly. I don't know. We'll finish those two branches in a second. And then it says down here that even the items that were made by the good person who was good was 3%. So that's 0.03. And then people who keep on this is 0.97, 97%. Okay, so here I need your help. So that's what that total should be. Let's do a little bit of math. If you have a calculator, please do this. Go 0.2 times 0.12, please. 0.2 times 0.12. 0.024? 0.024, like that? Is that right?
Yeah.
Okay. And then will you go 0.2 times 0.88, please?
0.2
times 0.88. Point what?
176.
0.176. Thank you. And then will you also then do 0.8, which is 80%? 0.8 times 0.03. 0.024. And then last one, will you go 0.8 times 0.97, please? 0.8 times 0.97. How much? 0.776. Okay, did we do all those right? Are my numbers right?
Okay.
think it's 0.8 times 0.03, 0.024.
I got 0.6424
Which one?
for return.
Here?
03, yeah.
That one? What'd you get?
I got 0.6424.
0.64. That's too high. 0.8 times 0.03. Try it. 0.8 times 0.03.
Oh, no, I got that.
Is that right now? Okay. Let me just. How about your? I just want to add something up real quick, make sure we're good. Plus 0.176 plus 0.024 plus 0.776. Did my math right. I like when I have this. Okay, so remember with a tree diagram, whatever branch you get on, you have the thing. So we did this plus this to give me 1.0. Agree? Now if I go here plus this plus this plus this, it also should add up to 1.0. If you do it on a calculator, not a decimal thing turned on, it should come out to just 1. Okay? And that's one of the things that tells you you have done the tree diagram correctly. Okay? A lot of errors on tree diagrams, people will get to here going, oh, 0.12 plus 0.88 plus 0.03 plus 0.97. Hey, mister, I got 2. Good. You should have. You have to multiply the branch to the branch in order to get the final outcome. Okay. So now, the last question on this. Given that an item was returned. Given that an item was returned. So, talking about this branch or this branch. Still with me? Make sense? What is the probability it was assembled by an inexperienced employee? Which one of these branches dealt with inexperience? The top one or the bottom one? Top, inexperienced, right? So it's this to this to this. So you have a 0.024 or a 2.4% chance that a returned item to your store or your factory was made by an inexperienced employee. Okay? So a tree diagram is a good way of seeing the representation. Tree diagrams where they don't become a really good thing is where you start creating like 4 or 5 choices out, so you have branches way far out in probabilities. But it still is a pretty good visual representation. And I know that there's programs you can get on the computer that allow you to do this pretty quickly. Okay? Okay, let's take a look at number 6. It says, each morning coffee is prepared for the entire office by one of 3 employees. Okay, I think we can do this. Okay, so problem number 6. So coffee is made by one of 3 employees. Everyone agree so far? So let's see if there's anything here that we need to do. Okay. Depending upon who arrives there, so it's made by one of 3 employees, depending upon who arrives at work first. So you have this person, this is Karen, who arrives to work 20% of the time or 0.2% of the time or early. And then Gail and Larry are each to arrive on half of the remaining mornings. Okay, so if Karen arrives early 20% of the time, that leaves the other 2 get there 80% of the time, and we're going to break up how much it is. So you have Gail and you got Larry, cable guy, right? So that's 0.40, 0.40. Okay, does that tree diagram make sense to the context of this problem? So Karen happens to get there 20% of the time early. Gail and Larry get there early. The rest of the time evenly distributed. So if I add up my tree, I got 0.2, 0.4, 0.4. They add up to 1.0. Is our tree diagram correct so far? Okay, the probability that the coffee is bitter when prepared by Karen is 10% of the time, 0.1. So she has bitter or the normal. What did I say, 0.1? So if it's not bitter, which just means you didn't clean the coffee pot, is really what it is. That means 0.9% of the time, or 90% of the time, when she makes it, it's fine. Okay? While the corresponding probabilities when it is prepared by Gail and Larry are 0.2 and 0.3 respectively. So Gail would be bitter 0.2. So that means that not bitter is 0.8. And then Larry was what? Point what? Help me out. 0.3. Thank you. Bitter 0.3. So 70% of the time Larry makes it, when he makes it, not bitter. Okay. So again, these are the probabilities if a person had made it. These are the percents, or and it's decimal, that it was either bitter or not bitter. Okay. So in order to make our tree diagram appropriate, I need to multiply 0.2 times 0.1. Calculator time, please. 0.02. Thank you. And then 0.2 times 0.9, please. Is it 0.18? 0.18. Thank you. And then 0.4 times 0.2 is 0.08, I believe. Is that right? And then 0.4 times 0.8 is 0.32. Am I correct? Help me out. And then 0.4 times 0.3 is 0.12. And then 0.4 times 0.7 is 0.28. Is my math right? Gosh, I hope. Is it right? So if you have a calculator, can you add this up for me? 0.02 plus 0.18 plus 0.08 plus 0.32 plus 0.12.
You got me stopped.
0.02 plus 0.08.
You're just doing these black ones. You got one?
I did it.
One.
I got 0.80.
You forgot something then. Should come out to 1.
It came up to 2.
Point. You have your decimals in the right spot? That's 28, 50.
Oh, yeah, you're right.
It comes to 1. Second one.
Oh yeah, this. How did I get 2?
Who knows? When you start dealing with decimals, it gets goofy. Your fingers start moving around the wrong way. All right. So let's see if we can answer these questions. Does everyone feel comfortable with how we generated the tree diagram? Okay, so if you arrive one morning and find the coffee bitter, okay? So the bitter is here, here, or here. Sounds like all three don't know how to make coffee appropriately. If you arrive one morning early and find the coffee bitter, what is the probability it was prepared by Karen? So Karen's branch is here, and the bitter is here, so 0.02. So you have a 2% chance that Karen was involved with that bitter day. Okay? What about by Larry? Larry's bitter 12% of the time. Boy, Larry just doesn't get how to make coffee. That poor guy. And then what is the probability? So what is the probability that it's not bitter at all? You just show up to work. So there's a not bitter. There's a not bitter. So if I add 0.18 and 0.32, I get 0.50. And then that's a not bitter as well. If I add 0.18, 0.32, and 0.28, I think I get 0.78. So you have a 78% chance that you're pouring your cup of coffee going, hey, it's not bitter.
That means once a week. It's most likely going to be
Wait,
bitter.
did you say 0.78?
0.78, yeah, because you go 0.28 plus 0.32 plus 0.18. The pink one's circled. That all right? Yeah.
So when you said this is at the very beginning, there half and half for Helen and Larry with 40.
So there was an 80% chance that either Karen or Gail or Larry got there early. They got there same percent of time. So it was 0.4 for Larry. All seen box plots at some point in time on a test or quiz. Whether you kind of saw what had happened with it, I don't know. Unfreeze it. All right. So box plots. Let's talk about these. So it's known as a 5-number summary. You have a minimum and you have a maximum. The lowest number and the highest number of a list of numbers. Make sense so far? Yeah. That's called your min or your max. Still make sense? You have a middle part of your data, which is called the median. Median means middle. Median is also sometimes referred to as Q2. The letter Q and the number 2. And then if you cut your data in half, then half of that data is called Q1. So the bottom quartile, or if you cut the top part in half, that's called the top quartile as Q3. Okay, so let's see if we can kind of walk through what this means. So this right here would suggest, I have a minimum of 10. Is that okay so far? And then it looks like I have a maximum of 85. Make sense? So, now what we do is we take all of our information and we cut it in half. So right here is our median. So 30 is our Q2, which is also referred to as the median, M-A-D-I-A-N. Okay? So what the median means is half your data is below it and half your data is above it. So the median cuts your data right in half. So then this right here is known as Q1. And this appears to be 20. This right here appears to be Q3, which appears to be 55. So let's say you were to look at like test scores of an entire class. You have someone who earned a 10 on it. You have somebody who earned a 85 on it because you're min and your max. The middle score is a 30, so pretty cruddy test, I think. So what that means is between 30 and 85, 50% of the tests are there. Between 30 and 10 is the other 50% of the test. Within this region right here, you have 25% of your data. You have 25% of your data, you have 25% of your data, and you have 25% of your data. So let's see how I can make this appear good. Let's go with highlighter. So this region here is 25% of your data. This pink region right here is 25% of your data. This blue region right here is 25% of your data. And then this green region here is another 25% of your data. So you're dividing your data into parts. Okay? You have a maximum value, you have a minimum value, which is your high score and your low score. Okay? You can figure out the range of it by subtracting the high score and the low score from each other. Okay, so the interquartile range, the IQR, is the interval that traps the middle 50% of the scores. So This right here is your inner quartile range, your IQR. It accounts for, and so it's Q2 or Q3 and Q1 as your endpoints. Whatever those values are, you subtract them. Okay? I think as we progress on this, it's going to start making a little bit more sense. So, any score that is 1.5 times the IQR above the quartile Q3, or 1.5 IQR below the quartile is called an outlier. So let's talk about this. Let's say we had given a test, and we gave it to all students. Let's say we have a couple hundred tests that we're looking at. We could easily say, okay, what's our best test score? What's our worst test score? Here's our median. And then if I were to take my IQR and multiply by 1.5, it might show that it's beyond as an outlier. So some of these scores are called extreme scores. They're far, far outside of your information. If I go back one board, if I find the IQR of this is just Q3 minus Q1. Q3 we said was 55. Q1 we said was 20. So if I go 55 minus 20, I get to 35. If I multiply 35, does someone have a calculator? 1.5 times 35.
Equals 15. I mean, 17.5.
17.5?
I don't know. I'll just guess.
I got 52.
52.5. So, if I add 52.5, we'll get there. So, if we're moving down, cut off our outliers, whiskers go out to the last number, not the outlier. Draw the whiskers to the most extreme score that is not an outlier.
Wait, it's 45.
It's 45.
No, that would be 35.
Did I get this? Was this 45?
Yeah, it's 45.
Okay. So what that means is if I add that 45 to that 55, that would be an extreme outlier. If I were to go that way, if I were to subtract it, I'd have an extreme outlier the other way. Okay, but this is a bad representation. Shame on us for doing it this way. Let's see, let's go down. You know what, I'm going with my own notes on this. All right, let's just make this very simple. Let's say I have this list of data. Still with me on this? Let's make a fox and whiskers plot off of this. Okay? So I need to find the middle of my, so this appears right now that I have a minimum of 3 and I have a maximum of 18. Everyone okay with that? How many total numbers do I have? I got 3, 7, 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 numbers. So in order for me to find the middle of my numbers, one, they have to all be in order. Are they all in order?
How did you get 37?
I made them up.
Oh.
I didn't like the example, so I decided to go off the cuff and do my
So
own.
you're gonna just basically
Do the whole thing on my own. Okay? So I have a total of 10 numbers up here. Is that okay?
Yeah.
Okay, so in order to find the middle of 10 numbers, I have to go 1, 2, 3, 4, 5, and 6. Those two are my middle. So technically how I find my very middle is I add those two numbers together and divide by 2. So 10 plus 10 is 20. 20 divided by 2 is 10. Yeah.
You could go cross out the left side and go to the other side, cross the right, cross the left.
Well, I'm not eliminating them yet. So because I have an even amount, I have to go 10 plus 10 divided by 2, which comes out to 10, which 10 is my median. And my Alright. I don't have time to finish. I apologize.